Have you ever stopped and thought about this? Somewhere above the clouds, right now, a commercial airliner is getting struck by a bolt of electricity powerful enough to vaporize a tree in an instant. And yet, passengers on board barely notice. Some don't even look up from their phones. Today, we're breaking down how airplanes survive getting hit by lightning. And I promise, after this video, you'll never look at a storm cloud the same way again. To understand the scale, think about a single lightning bolt. It can carry around 300 million volts and roughly 30,000 amps of current. Its core temperature can reach nearly 50,000 degrees Fahrenheit, hotter than the surface of the sun. That much energy hitting a thin aluminum tube, packed with fuel, wiring, and human beings, should be catastrophic. By common sense, that aircraft should fall out of the sky. But physics says otherwise. And the reason lies in over a century of aviation engineering, hard lessons, and careful design. In the early decades of flight, lightning was genuinely terrifying. Aircraft were smaller, less understood, and far more vulnerable. In 1963, Pan Am Flight 214 was struck by lightning over Maryland. The strike ignited fuel vapor near a wing tank, and the aircraft was lost. That tragedy became a turning point. Engineers realized that surviving a strike wasn't about avoiding lightning. It was about controlling exactly what lightning does once it arrives. Investigations after that crash reshaped fuel tank design, bonding standards, and lightning protection rules across the entire industry. Out of that work came formal certification standards that every new aircraft design still has to satisfy. Engineers mapped the fuselage into strike zones, based on where a bolt is statistically likely to attach, travel across, or exit. Each zone carries its own current requirements, and every panel, seam, and fastener in that zone has to be tested against the simulated strike before regulators will approve the design. It's not a guess anymore. It's a certified, repeatable standard applied to every airliner built today. And strikes are far more common than most passengers realize. On average, a commercial jet is struck by lightning roughly once every 1 to 2 years of active flying. Across the global fleet, that adds up to several strikes happening somewhere in the world on any given stormy day. Since those 1960s redesigns, there hasn't been a confirmed case of a modern airliner being brought down by a direct lightning strike. Strikes have become almost routine, and modern aircraft are built specifically to shrug them off. So how does all that electricity avoid destroying the plane? The answer lies in 4 core principles. 1. Conductivity. The aircraft's outer skin is built to carry current efficiently. 2. The Faraday cage effect, keeping electricity on the outside instead of the inside. 3. Controlled attachment and exit points, directing where lightning enters and leaves. 4. Continuous discharge, preventing dangerous static buildup before it ever becomes a problem. Think of the airplane less like a fragile target and more like a moving lightning rod, engineered on purpose to handle the hit. You've probably heard the common explanation. People assume lightning simply fries the plane's electronics or burns a hole straight through the fuselage. That explanation is incomplete. What actually happens is far more elegant. A commercial airliner's skin is mostly aluminum, and aluminum is an excellent electrical conductor. When lightning strikes, the current doesn't need to punch through the metal to find a path. The metal already is the path. Electricity spreads rapidly across the outer surface and searches for the fastest route back out. This is where the Faraday cage effect becomes essential. A Faraday cage is any enclosure made of conductive material that channels an external electrical charge around its surface rather than through its interior. An airplane fuselage behaves almost exactly like one. As current flows across the aluminum skin, the electric field inside the cabin stays close to zero. Passengers, wiring bundles, and hydraulic lines sitting inside that shell remain largely shielded from the enormous voltage traveling just centimeters away. That's the real secret. The plane isn't blocking lightning, it's guiding it. There's a specific term for part of this behavior, the skin effect. At the extremely high frequencies present in a lightning discharge, current naturally prefers to travel along the outer surface of a conductor rather than through its core. That's actually useful here. It reinforces the same outcome the Faraday cage effect already produces, keeping the violent part of the strike confined to a thin outer layer of metal instead of driving deep into the structure. 2 separate physical principles, working in the same direction, for the same protective result. But that leads to the real question. Where exactly does lightning enter and exit? Almost every strike attaches to a sharp extremity first. The nose, a wingtip, the tail, or an antenna. These points act as natural attachment sites because they concentrate electrical field lines more strongly than a flat surface would. Once current enters at one of these points, it travels along the skin toward another extremity, usually the tail, where it exits back into the atmosphere. Engineers call this the entry and exit path, and virtually every aircraft is certified against a defined set of these possible strike zones before it's ever allowed to carry passengers. One of the biggest fears people have involves fuel. If lightning enters near a wingtip and fuel tanks sit inside the wings, why doesn't the tank ignite like it did in 1963? This is where design changed permanently. Fuel tank structures are now sealed and bonded so tightly that stray sparks essentially can't form inside them. Every panel, fastener, and access point is electrically bonded to the surrounding structure, eliminating small gaps where a spark might otherwise jump. Fuel vapor space is also managed carefully, and inerting systems on many modern aircraft reduce oxygen concentration in the tank, making ignition far less likely even if a spark somehow occurred. The lightning takes the metal path, not the fuel path. There's another quiet defender working before the storm even arrives: static wicks. If you've ever looked closely at the trailing edge of a wing, you may have noticed small thin rods sticking out. Those are static dischargers. As an aircraft moves through the atmosphere, friction with air molecules and ice particles builds up static electricity across its surface. Left unmanaged, that charge could interfere with radio communication or, more importantly, increase the likelihood of triggering a strike. Static wicks continuously bleed that charge safely back into the air, keeping the aircraft's electrical potential low and stable throughout the flight. Not every part of the aircraft is naturally conductive, though, and those spots need special attention. The nose radome, which houses the weather radar, is made of non-metallic material so it doesn't interfere with the radar signal. To keep it from becoming a weak point, manufacturers embed a diverter strip, a thin conductive strip bonded to the surface, that grabs the strike and channels it safely into the metal fuselage behind it. Cockpit windows face a similar problem. They're heated electrically to prevent icing at altitude, and that same conductive heating film doubles as a path that keeps a strike moving across the glass instead of concentrating in one fragile spot. Modern aircraft add another layer entirely. Many newer airliners use composite materials instead of solid aluminum for large parts of the fuselage and wings, and composites don't conduct electricity nearly as well as metal. To solve this, engineers embed a fine copper or bronze mesh directly beneath the composite surface. That mesh recreates the same conductive skin that aluminum naturally provided, allowing composite aircraft to handle a strike using the exact same Faraday cage principle, just with an artificial conductor layered in place of the metal. So what actually happens the moment lightning strikes mid-flight? Passengers typically hear a loud bang and see a brief flash. The aircraft itself experiences almost no disruption to its flight path. Current sweeps across the skin in a fraction of a second and exits through the tail, leaving behind, at most, a small scorch mark or a tiny pit at the entry and exit points. Cockpit instruments are hardened and shielded against the electromagnetic pulse a strike generates, so critical flight systems continue operating normally throughout the event. In the cockpit, the response is almost anticlimactic by design. Pilots are trained to expect the bang and flash as a routine weather flying event, not an emergency. They scan their instruments, confirm engines, hydraulics, and electrical systems are still reading normally, and continue the flight as planned. There's no dramatic maneuver, no sudden descent, no mid-air crisis. The airplane was built to absorb exactly this moment long before it ever left the factory floor, and the checklist reflects that calm. After landing, procedures kick in immediately. Any aircraft confirmed to have taken a strike undergoes a mandatory inspection. Engineers examine the suspected entry and exit points, check for pitting, and inspect nearby fasteners, antennas, and static wicks for damage. In the vast majority of cases, the inspection finds nothing more than cosmetic marks, and the aircraft returns to service the same day. Every time lightning hits a passenger jet at 35,000 feet, it feels like it should be a disaster, but it's not breaking the laws of physics, it's using them. Conductivity, controlled attachment points, the Faraday cage effect, continuous static discharge, everything exists in precise, deliberate balance. To me, that's the real beauty of aviation engineering. Not luck, but exact calculation and respect for the forces trying to tear the aircraft apart. And now I'm curious, have you ever wondered why airplane windows are always round instead of square? I've already made a video about that.